Welcome to Insight, a brand new series profiling some of the latest advancements in science, technology, and research. We'll explore this fascinating world through the works of various academics and professionals from around the world. So join me as we embark upon an eye-opening journey of insight. In today's program, we have with us a physicist who works in the field of nanophysics. Dr. Mudassar Rashid is an experimental physicist at King's College London. He is also the chairman of AMRA. AMRA stands for the Ahmadiyya Muslim Research Association. Its purpose is to support Ahmadi researchers in becoming world-class researchers. Mudassar is currently working towards building, wait for it, novel optomechanical experiments for exploring macroscopic quantum physics, nanothermodynamics, metrology, and force sensing. Confused? Don't worry, so am I. And so, we're going to attempt to break this down into digestible chunks. We will also look at Mudassar's own research to better understand his work, and we'll walk you through the career paths one could take to get into the field of scientific research. But before all that, let's take a short look at a day in the life of Dr. Mudassar Rashid.
Hi, my name is Mudassar Rashid. I'm an experimental physicist working at King's College London, and that's where we're at today. I'm going to be telling you what I do through the day, who I work with, and you'll be meeting them all, whether in the lab or in the office. So let's go have a look. So we're at the Strand campus, and the Strand building has 8 floors and 3 base floors. So we're going to go to one of the first base floors to visit the lab that I work in. So these are newly refurbished labs that are occupied by various nano-optomechanics and photonics groups in King's College physics department. And we'll be visiting one of them where I work. These are also clean room environments. So you have to be very careful, of course, with what you wear and what you take inside. So everyone has their own designated shoes. And I have my own. And so we wear these. And then I'm ready to go in the lab. So in the lab, as you can see, it's a very pressurized environment. It's AC controlled. And it's to make sure that our lab equipment and everything that we have here is in this perfect environment because we work on a lot of sensitive equipment. So once I'm in the lab, the first thing I really want to do is check up on the experiments that we have running, make sure that I still have the particle that we trapped. So you have over here 2 different types of ion traps. So these are electrodes that generate oscillating electric fields to levitate microspheres. So this is the one that we're going to use today because it actually has a trapped particle inside. And so the first thing I'll do is I'll switch on the lasers, make sure it's all ready. You can see the green light coming out. And then we can have our camera connected. And we are using a microscope essentially to zoom in to this microscopic object and having a look at its motion. And that's what we have over here. So this is actually a levitated, hovering object. And to convince yourself that that's what you're looking at, I can zoom out. And it's this beautiful, beautiful image that you have of 2 electrodes, metal rods essentially. And there's 2 metal rods on the top as well you can't see, to which we've applied electric fields. And here you have this sparkling little microsphere trapped, hovering in vacuum, in fact. And so a lot of that humming sound you're hearing is vacuum pumps that are evacuating these chambers. So they're very, very noisy generally. We have very specific electronics to control all of this motion. So now, this is all wonderful, but this is not science. This is nice to see. We actually want to take the motion and analyze the motion. So today's job actually was to expose this particle to a different kind of noise field. So now I'm going to change the camera, which is a CCD, to a photodetector. It allows us to detect the motion of the particle really, really fast. And you'll see the consequences of that. So what happens is that the light that illuminates the particle is scattered. That scattered light is collected by the microscope and becomes incident on the photodetector. The photodetector records the light information and encodes it into an electrical signal, that electrical signal carries through these different filters and electronics, and I can now detect the motion of the object on the screen. So now that we've looked at the lab, we're going to look at where I work in the office and where I sometimes have to have meetings and actually have a coffee. So let's go upstairs.
Level 7.
So we've arrived at level 7, which is the physics department. For those that don't know where King's is, let's have a quick look. And this is a really wonderful view and puts a perspective to where King's College London is situated. This is beautiful cityscape. So there's the Millennium Wheel and the Somerset House. And King's is really in the middle, right next to the River Thames that you can see in the far background. One of the advantages being that people, when they visit anywhere in the country, they have to stop in London, and allows us to have these meetings with collaborators, with academics around the world. So today's plan really was to make sure that the experiments were running and then have a catch up with a few students. One of them is working off-site and is currently analyzing a bit of coding for me for the experiments that we're running. And then reading some papers, which is a very important part of the life of an academic. And so that is how I spend most of my days between labs and the office, and talking with the students and working together as a team to try and find and solve some of the fundamental problems in physics. So I hope you've enjoyed and giving you a taster of what physics is like, nanophysics specifically, and what a lab for nanophysics looks like. Look forward to seeing you again. Thank you.
Viewers, as you have seen a short introduction into the life of Dr. Mudassar Rashid, you may be wondering, well, what exactly is nanophysics and what impact could it have on me? So let's find out. Dr. Mudassar Rashid, what is nanophysics and how could it impact the average person on the street?
So nanophysics is really about understanding the laws of physics at the nanoscale. And the scale is around the size of what you might find viruses or bacteria in. So actually, the physics that happens at this level is very important for us because it's not just related to our body, but also technology that we use on an everyday basis, we often find is actually at that scale. So it has a massive impact on us. And understanding how these laws actually work allows us to, one, take advantage of them, but also better understand nature.
And so, I mean, how could a school or college student get into the field of science or research or nanotechnology?
So most universities now have some sort of focus towards nanotechnologies in general, whether you're doing chemistry, computer science, or physics. Really, it comes down to doing a degree, doing some sort of sciences at say, pre-undergraduate level, so at school or college, being really good at that. Maths is very important. And then that should allow you to then get on to doing an undergraduate degree in physics, for example. And then from there, you can divide into a subfield of nanophysics.
So could you delve a little deeper into what type of subjects one would take specifically and what type of grades would be required to get into the field?
So once again, as I said, sciences, so chemistry, physics is really important. But then as well as maths. And you should be really aiming for relatively high grades because these are quite demanding subjects, but also very competitive. And so in the UK, for example, the grade criteria can vary from B to an A, at A levels to get into a good university where you can then study this.
So your specialist area, I understand, is optomechanics. Firstly, could you break that down for us in sort of layman's terms and also maybe explain why you decided this was going to be the thing you were going to spend the next several years of your life on?
Yeah, so optomechanics, opto refers to light. And mechanics, of course, is in reference to mechanical objects and their motion. And so optomechanics is actually looking at how light impacts your mechanical objects and their motion. And I didn't really actually know about this when I started studying physics. I was interested in light. I was fascinated by light in terms of what you could do with it, how it was used. And it just so happened that I came across a paper as an undergraduate student. And one of the professors there was actually doing research in this, in what is known as optical tweezers, and how light was actually impacting these macro objects, specifically bacteria and viruses. And I was very fascinated. So I asked him, and I did some research with him, and I learned more through that, and that captivated me. And then I did a more specialized master's in what is known as photon science from Manchester University, which allowed me to really see light and its uses in medicine, in chemistry, in industry, in physics as well, and how it impacts us all, in every sphere of our lives. But at the same time, I became very, very interested in fundamental problems that actually optomechanical systems were trying to address. And one of these problems was, this quantum mechanical divide, or the laws of thermodynamics at the nanoscale, and all these kind of things ultimately led me to focusing more and more towards optomechanics.
Okay.
As a subfield.
So, I mean, generally speaking, solutions tend to be sought for pre-existing problems. Did your research attempt to address any particular problem?
So, it's the setup of optomechanics allows you to actually probe a regime that we don't really understand very well. And this is the divide between, say, the very microscopic, the atomic and molecular scale, and the macro scale that we have in our everyday lives. The laws that govern the atomic scale, known as quantum mechanics, are very different to some extent what govern the macroscopic scale. So, if I throw a ball, when I throw it at a wall, it's going to bounce back. But at the quantum scale, if I throw a quantum ball, there's a probability it will actually go through the wall. And this is really bizarre. And why is it that those laws don't work the same way as they do in the macro scale and vice versa? And to understand if there's such a divide exists, these optomechanical systems were perfect because they use massive objects that are big, and they can access this quantum world as well. Or at least that's the attempt. So this captivated me as a problem, and that's what I've been working towards as well.
And so in your research, I mean, have you ever sort of experienced any kind of scientific breakthroughs?
So it's really what you don't expect is the exciting part sometimes, So when I was building this experiment, and others around the world as well were also building this for various applications and work, started to discover that these objects that are levitating, so I use light to levitate these objects, were actually not only just moving up, down, left, right, and back and forth, they were actually spinning and rotating. And that was really fascinating. So I just happened to see a weird signal in my data. And I was, okay, what is this? I have to figure this out a bit more. And I looked deeper in. It turns out that the object I had trapped, that was levitating, was actually doing some sort of precessional motion. And as I studied this, so no one had seen this kind of motion in these objects before. And as I studied these, I discovered that actually they can be amazing sensors. So if you put a small force on them, apply a small force to them, you can detect that force, where you may not be able to do that, say, in normal devices or normal sensors that we might find in the industry right now. So that was a very exciting discovery. So the next future research that we're doing is really trying to build on that as well and capitalize on it.
Okay, and so in terms of Joe Public, once again, are there any benefits or practical applications that your research could eventually find its way trickling down into?
So this is always tricky, right? Because a lot of the work that I want to work on is actually very blue sky. So it's fundamental research. But as it happens, over the last decade or so, we found that these mechanical objects that are at the nanoscale have very interesting properties, and so applications as well. So one of them, for example, is exploring them as a heat engine device. Something that converts heat energy from its surrounding to mechanical motion, something useful. The other alternatives have been where as I said earlier, where you apply an external force, like when you accelerate an object, you feel that acceleration. Well, we need accelerometers. These are the sensors that you have in your mobile phone. and we need them as sensitive as possible. It turns out these objects that are levitating are incredibly sensitive to acceleration, to motion, essentially. And so we're actually now working on miniaturizing a lot of this stuff for real world application, where we'll work with industry to actually see if we can create these devices. You never know. Hopefully, your mobile phone will have a levitating sphere one day. I mean, it's still far in the future, but that's the hope, that we can improve on the devices we currently have and maybe branch out into new ways of doing it.
Absolutely fascinating. Thank you so much for your insights. Now, viewers, we will move on to the next part of the program, where Dr. Mudassar Rashid will showcase his research in the form of a presentation. So let's take a look at it.
I'm interested in trying to understand the laws of physics at the nanoscale. This is the scale at which you will normally find viruses or very small bacteria. It is also the sizes at which modern transistors exist, something like 7 nanometers. So to probe this regime, I've built an experiment known as the ion trap. This uses high voltages, oscillating electric fields, to levitate charged objects. We take very small charged glass spheres, about the size of 1 micron, and levitate them in this ion trap in a vacuum. As you can see, its motion is not so smooth, partly because of a camera effect, but additionally, the particle is experiencing high levels of noise from its surrounding. At the nanoscale, noise becomes a very important feature. As you walk down the street, your movements are steady and precise. Unless you are ill, you're not going to be moving to and fro. The surrounding environment, like air molecules, rarely make an impact on your motion. But what happens if we shrink you down to the nanoscale? You are now much smaller and closer to the size of the particles surrounding you. Your environment, like gases made of air or fluidic like water, have a discernible effect on your motion. The collisions from gases like gas particles and liquid molecules impact your body, and therefore your body moves to and fro in a random sort of walk. This random walk actually is an imprint of a type of noise you are in. A perfect example is the Brownian motion. Imagine this yellow dot being some sort of nano machine. It will experience random collisions as it moves through space, through its environment. So its motion will actually have a visible signature of its randomness. I'm trying to understand how noise at this nanoscale works and what kind of impact it may have on the laws of motion, but also on the nanotechnologies that we may want to make. Currently, by understanding this noise, I'm exploring new types of heat engines that might exist for nanotechnological applications. By definition, a heat engine is a system or device that takes heat energy and converts it into mechanical energy. Imagine a simple car engine. Its regular, precise movements are no longer so smooth when shrunk down to the nanoscale. In fact, moving parts in the nanoscale are not so readily achievable in this manner. So we have to come up with a completely new way of creating these types of engines. Let's try to understand how this flow of heat and energy might work at the nanoscale. Energy from, say, a hot bath, like a hot gas or an explosive liquid, is used by an engine to generate mechanical motion. In fact, the second law of thermodynamics tells us that there is no process possible whose sole result is the complete conversion of heat into work. There is always some sort of loss of heat. This makes sense. We see that all the time. But at the nanoscale, there is a possibility of violating this important law of thermodynamics, even momentarily. You can actually take this lost heat to generate mechanical energy as well. The long-term average effect is that there's always some loss. However, there is, for short periods of time, we can access this heat loss for our benefit. Therefore, at the nanoscale, mechanical devices have to be reimagined in a different way. Most of these types of heat engines are things like nanowires or solid-state diamonds that are being explored as possible nano engines. In our lab, at King's College London, we're using levitated spheres. At the nanoscale, we're realizing this by using motion of a charged particle to charge a battery, for example. Its motion of to and fro converts energy from a hot circuit into a battery. This may be a powerful way of converting heat that might happen, say, in microprocessors to something that's useful. These are early days, and still a lot of details are still being worked out. However, ultimately, I'm interested in developing new types of probes that allow me to better understand how physics is modified at the nanoscale. This includes building new types of electronic filters, force sensors, and physical simulators. The heat engine enables us to study noise at this nanoscale in different ways. But one very powerful advantage of this setup is its integratability with electronic circuitry. The benefit would be that we are able to directly cool overheating chips, which is a major problem in the computer industry. But maybe one day we may have nano engines in every mobile and computer chip.
Viewers, as you saw there, scientific research covers a vast array of topic areas and subtopic areas, each with a plethora of applications to address real-life issues. This is now the end of the program today, and I hope now, like me, you too are also a little more enlightened into the wonderful world of nanophysics. Join me next time for another episode of Insight.